I uploaded 2 practice exams from spring, from last semester and the semester before that. The practice exam, it's a PDF file. At the end of the file, you will have the key. If I'm you, I wouldn't look to the key. I would first kind of take one away, take it as if it is an exam, then look at the key. I also, and both of those are in Moodle, in topic I think 4, and it is called practice exam, in a folder called practice exam. And I also uploaded something called the information page. The information page is the first page of the exam. What I'm going to give you as periodic table, as equations, as tables, constants. So from now, you know what exactly you need to learn and what exactly going to be given to you. So it's already there from now, print it out, get used to the periodic table that you will be given. So those are the practice exam and the information page are a Moodle. Under practice exam, I already uploaded the key for the 3 worksheet. Still, the worksheet for moles, molecules is going to be uploaded sometime on Monday. One other thing before we go in with the chapter 3. The only thing that I forgot talking about when I was talking about ionic and covalent, we talked that ionic compounds take place with 1A, 2A, 6A, and 7A, and the non-metals of that. The only thing that I didn't talk about is that we said that group 1A, all of them are metals, except hydrogen is not a metal. And usually hydrogen, when it make compounds with group 6A, 7A, 5A, 4A, it make covalent bond. For example, water, there is a covalent bond between oxygen and the hydrogen there. For example, in methane, since hydrogen always do a covalent bond with group 6A, 4A, 5A, 6A, 7A, so those bonds are covalent. And I think I forgot to tell you that during the process of explaining covalent and ionic. This is an exception. So whenever you see hydrogen making compound with any of those, it's going to be a covalent bond, not an ionic. Okay? Now, let's go back to chapter 3, which we were talking about stoichiometry, how to calculate the mole, the number of mass, molar mass. And we're going to start with this eye clicker. So, capsaicin is a compound that gives the hot taste of it to chili peppers. And it has a formula. This is the formula. Calculate the number of moles of carbon in 55 milligrams of capsaicin, knowing that the molar mass, this is the molar mass of that molecular formula. I'm going to give you 3 minutes because it needs calculation. So go ahead. You can talk to each other. You can ask your friend, the one behind you, next to you.
Hey.
How does the 55 milligrams come into play?
So you calculate the number of moles of the substance itself.
Right.
So you do 55. So there's 55 milligrams. It's 55 milligrams. Okay, so 55 milligrams times 1,000, you get grams, right?
Okay.
So it's probably not A, then divided by 305.42 grams per mole. So, wait, yeah, okay, so 3, 4, 2. 55 divided by 1,000. There we go. Divided by.
Yes.
That mole mass is for the entire capsaicin molecule.
Yes, this is the molar mass of the whole molecular formula of C18H27 and O3. Yes. I'm asking about the number of moles of carbon. Okay? I'm not asking about the number of moles, how many moles I have of this. And by the way, this is also what happened during exams, that we'll ask you, for example, about the number of moles of hydrogen or nitrogen inside the compound, and all what you're doing is calculating the number of moles of the whole molecule. And that's not right. Okay? So I'm going to turn off now. No? Okay. I'm going to stop it at 4. At 4 minutes.
If you can know, yeah,
I
like,
think it's actually B. Alright,
Why?
so it's 55 milligrams. So 55
Right,
milligrams to convert it to grams divided by 1,000.
okay.
So that's how many grams. Multiply it by the molar, or divide it by the molar mass.
Divided by the molar mass?
I think so, right?
Why are we dividing?
So it's grams per mole. So it's
Okay. Stop it right now.
I think it's gonna be
And
easier
check.
if we're doing.
What
Do
do
we
you
not know?
think about this? I have A, and the most popular answer is C, and the right answer is B.
Good
Okay,
job.
let's
There
see
you go.
how
There
long-
you go.
how come.
that's what's
Okay.
up. That's what's up.
So if you choose anything other than A, than B, either you didn't convert it from 555 milligrams to grams. This is one of the mistakes. So one of the choices is you didn't do that. The second thing is if you calculated the number of mole of the whole
So
compound,
then
the
you
whole
divide it
molecule, not the number of
by
moles
the
of
molar
carbon.
mass to get the number
The
of
other
moles
mistake
of that
is
stuff.
if you use
For every
Avogadro's
one
number
mole
and you thought you're
of
calculating the number of
capsaicin,
molecules
there's
from the
18
atom.
moles of carbon.
So all the other choices is
Right.
one
You
of
did
these
it times
mistakes.
18.
Yeah,
Okay?
times
So let's
18.
get
So you
started how to solve this. So our first thing is we need to calculate the number of moles of carbon. The first thing that you need to know that the number of moles of carbons, in this molecule equal 18 times the number of moles of C18H27 and O3. Okay? So once you calculate the number of moles of capsaicin, you multiply it by 18, that's the number of moles of carbon. So I'm going to start doing 18 and begin calculating the number mole of capsaicin. So I have 55 milligrams. So first I have grams, I want to go to moles, right? So we said to go from gram to mole, we're going to multiply by the molar, to go from grams to mole, we have to divide by the molar mass of the compound. But first, I have it in milligrams. I have to convert from milligrams to grams. So 55 milligrams, and the conversion factor from milligram to gram is 10 to the minus 3 grams over 1 milligrams. So now, in grams. Now I want to calculate the number of moles. So the number of moles I have to divide by the molar mass, which is 1 mole has 305.42 grams, which is the molar mass. Mainly I'm using N equals the mass over the molar mass. I know the mass, I'm dividing by the molar mass of the whole compound. And this is where I get, if I do the calculation, 1.8 times. So if I multiply those two numbers is going to be 1.8 times 10 to the minus 4. When I multiply by 18, that's going to be 32.4 times 10 to the minus 4 moles of carbon. So this is one of the most common mistakes in exams. We ask you about the number of moles of one, like carbon or hydrogen and nitrogen, and most of the class just stops at the number of moles of one of them. The other one, the other mistake that sometimes we don't ask you about calculate the number of moles of carbon. We're gonna ask you calculate the number of atoms of carbon. So it is the same process, but here you have to change it from moles to atoms. That means to multiply by Avogadro's number. Okay? I think I will have some of those, so practice more on this topic about how to go from grams to moles to all of these other stuff. Now, sometimes you'll be given percentage of mass. For example, the percentage of mass of this element in this compound, and the way to calculate the percentage, I'm giving here an example, calculate the percentage of carbon in C3H8. So the way to calculate the percentage of carbon equal the mass of carbon in this compound over the total mass. And since here I'm just talking about C3H8, it's the mass of carbon, which is 3, the molar mass of carbon, because I have 3 carbons, over the total mass of the compound, which is mainly the molar mass of the compound, which is 3 times the molar mass of carbon, plus 8 times the molar mass of hydrogen. So it's 3 times 12.01 gram per mole, over 3 times 12.01 gram per mole, plus 8, the mass, the molar mass of hydrogen, 8 grams per mole, multiplied by 100. And here definitely the whole thing is multiplied by 100, and that would be 81.72%. So if the percentage of carbon in this is 81.72, what is the percentage of hydrogen? The percentage of hydrogen is 100 minus the percentage of carbon. And this is applicable because I have, in this case, because I have only 2 atoms. This compound is consisted of 2 atoms, carbon and hydrogen. If I have carbon, hydrogen, and oxygen, I have to calculate either the hydrogen or the oxygen. Then I do 100 minus one of the other elements there. Okay? So it's 100 minus 81.72%, and that's ending me up to 18.29 of hydrogen. So that's it, so 18.28 of hydrogen. Okay? So this is how we calculate the percentage of mass in a compound. Now our next topic is empirical formula. How to calculate empirical formula. I'm going to wait just a minute until everybody finishes writing. Still writing. Okay. Now empirical formula. What is an empirical formula? An empirical formula, okay, let's say I was working in the lab and I get a compound. I don't know what is that compound. I don't know if it consists of carbon, hydrogen, what it is exactly consisted of. So usually we send those compounds to elemental analysis or any type of other analysis, and that lab or the analysis that they do in that lab, they will burn that compound, give me how much carbon, hydrogen, oxygen, sulfur is there. Now, if the compound is consisted only of carbon and hydrogen, my result's gonna end up back to me only percentage of carbon or hydrogen. If it is sulfur and oxygen, it's gonna be percentage of sulfur and percentage of oxygen. From there, I'm gonna do some calculation to find the empirical formula. That's what we call the experimental formula or empirical one. That empirical formula, let's say my compound have carbon and hydrogen. Okay? Well, what I'm gonna get from that empirical formula is the ratio of how many carbons I have to how many hydrogens. But that doesn't imply that this is the molecular formula. The molecular formula gonna be determined using the empirical formula and the molar mass of the compound. And this is what we're gonna learn today. How to get to this empirical formula from the results that I'm gonna get from the lab, and how to go from the empirical formula to the molecular formula. So the empirical formula is the very basic formula which is only give me the ratio of how much I have carbon to hydrogen, but not the one that I'm gonna see in the molecular form. Okay, let's start with an example. For example, hydrazine is composed, so I have this compound, I send it to the elemental analysis, and what I get back that I have 87.42% nitrogen, 12.58% hydrogen, and the molar mass of this compound is 32 grams per mole. Now, how I'm going to deal with that? First of all, we need to understand what is 87.42%. This result is telling me that you have 87.42 grams of nitrogen in a 100 gram of that compound that you sent me, that I sent to the lab, okay? And it's telling me I have 12.58 grams of hydrogen in the 100 grams that I sent, okay? So the way that we can figure out the empirical formula is by calculating from this mass the number of moles of hydrogens, the number of mole of nitrogen. Then we're going to go through steps to get to the empirical formula. So the first step is to calculate the number of moles of nitrogen, which is mass over the molar mass of nitrogen. The mass that I have in that compound is 87.42 grams over the molar mass of nitrogen, which is 14.01 grams per mole. And I'm going to get 6.240 moles. This is how much nitrogen I have. Then I'll do the same calculation. I'm going to calculate the number of moles of hydrogens, which is the mass over the molar mass. I have 12.58 grams of hydrogen in this compound, and the molar mass of hydrogen gram per mole. So the number of moles is 12.48. This is how much I have nitrogen and hydrogen in there. Now the next step is I'm going to say, okay, I have 6.240, and I'm going to have the hydrogen to be 12.48. So my next step is I'm going to find in this formula the smallest number, which is 6.24 in this case, and I'm going to divide the whole numbers in the formula with the smallest number. And if I do so, what I'm going to get is NH2. So if I divide, yes? This is not an empirical formula. This is just a step to the empirical formula. The empirical formula will never have an integer or decimal point or anything. That's not right. We're going through steps, and I'm going to comment on that. So this is just a step to go to the empirical formula. Now this is the one in red is the empirical formula. So empirical formula can never have 1.9, 1, 2 point something. It's going to be an integer. Now the question is, what if this calculation lead to 1.3? Let's say this is the calculation. This is what the calculation leads us. And 2.9. In this case, after dividing, you get those two numbers. What you need to do is begin thinking about rounding up. If this number is less than 5, you're going to make this number 1. If this number is greater than 5, you're going to round it up to 3. Okay? So if you have after division something like this, that wouldn't be considered the empirical formula. You need to do the rounding. And from there, now this is the empirical formula. Now there is some exception if we have 1.5, 1.25, and we're going to talk about this in a bit. Okay? So the empirical formula can never have decimals or like fractions or things. We need to fix that to get the empirical formula. Let's go back to what we got, which is NH2. If I look to the NH2 there, and I calculate, can somebody calculate the mass of NH2? Really fast. 16. So 14 plus 2, it's 16. But the lab told me, after I get the result, it told me that the molar mass is 32 grams per mole. So this is the empirical formula. But the mass, the molecular formula, the mass of the molecular formula is 32. And this is how we go from the empirical formula to the molecular formula. The molar mass, I'm going to insert in here. So usually the empirical formula is going to be multiplied by a certain factor x, okay? And the molar mass of this compound should be equal to the molar mass of the molecular formula. So let's say the molar mass of this is Mn2 plus 2MH multiplied by X, and it should be equal to the 32 grams per mole. Okay? So we just said that the mass is going to be 14.01 plus 2 times 1.008. X equals 32. We're solving one equation, one unknown. And in this case, X is going to be equal to 2. And then that tells me that the molecular formula is NH2 multiplied by 2. Therefore, it is N2H4. And this is the molecular formula of hydrogen. So we went from the empirical formula to the molecular formula using the molar mass. So your first step, whenever you get percentages and you're doing the empirical formula, is first calculate the number of moles of everything in there. After that, divide by the lowest number. After you arrange it in the molecular formula by the lowest number, then take care whether you need to round off if you have 1.9, 2.9, or something like that. And after that, when you get the empirical formula that has no integers, no decimals or fraction, it's all integers, at this point, you look to the molar mass, and from the molar mass, you can calculate the molecular formula. Okay? Get the idea? Okay. There are a lot on OWL. The more you practice, the better you'll get. The better you'll do it faster. So please practice. It's so easy to see me doing that, but when you're doing it yourself, it may take you more time to do that. So practice. Please practice on OWL on this. Now, let's do one. And I'm going to stop it at 3 minutes.
Let's see.
So I have C as the most popular answer being 81%, and yes, C is the right answer. But let's see, let's do the calculation and see. First of all, definitely B. I just put B there because definitely nobody should choose B. Because we just said no way that an empirical formula will have 6.16 or 6.5 or something. That's not an empirical formula. That's just a process to go to the empirical formula. So B could never be a choice for an empirical formula. Now, let's get started. So first of all, I'm going to calculate the number of moles of carbon, which is the mass over the molar mass. I have 74.0, always 12.01, definitely that's a gram per mole. And the answer for this is going to be 6.3 moles. Now the number of moles of hydrogen is the mass over the molar mass, and it is 8.6265 over 1.008 grams per mole, and that's a gram, and that's the number is 858. Number of nitrogen, grams over the 1 gram per mole, and that's going to be 1.244. 1.238 moles. Okay. Now I have all these numbers. I'm gonna put them 6.16, 8.58, and nitrogen being 1.238 in here. But that's definitely not the empirical formula. I have to divide with the smallest number in there, which is this one. So I'm going to divide this number and this number and this number by 1.238. So that's going to end me up with carbon 4.90, hydrogen to be 6.93, and nitrogen 100. Okay, now I have decimals in there. Okay? And I'm going to look there and say, okay, I have kind of to round. So carbon is 4.9. 9 is higher, more than 5, so I'm going to round it up to 5. 6.93, that's a 9. So I'm going to round it to 7, and nitrogen to 1. So this is the empirical form. So this is how, in this case, you're not given the molar mass of nicotine, so you can't, or the molecular weight of nicotine, so you can't go from the empirical formula to the molecular formula. And the question is about the empirical formula. Okay? Now, there are cases, for example, when we have something like this. After you do the division, you end up with 1.5. In this case, you have to multiply. To get to the empirical formula, you don't round this up to 2 or round it to 1. What you're going to do is multiply the whole thing by 2. And this is your empirical formula. Okay? So when you have 0.5, you don't round up. You don't round it off to either 1 or 1. Sorry, that's going to be 2. Sorry. Oh, no, that's not. You don't round it up to 2, or you don't round this number to 2. Okay? You multiply the whole formula with 2. So with this, we're done from, yeah. Okay, so if you have, for example, 4.9, 4.7, 4.8, you're going to round up. It's only when it is 4.5 when you multiply by 2. If it is, for example, 4.3, 4.2, you're going to round it to 4. This, you're going to round it to 5. It's when 4.5, and another case is, for example, 4.25, which is 4 and 1/4. This is when we have also to multiply by 4 there. But for 4, the most common example that you're going to see is 1.5, where you have to multiply instead of rounding. Okay? So 4.2, 4.1, all of these you're going to round and it's going to be 4. Only 4.5 is the place where you're going to multiply. From the examples that I gave. Okay, by this we're done from the empirical formula, and we're gonna get started with stoichiometry and limiting reagent or reactants. So let's start. First of all, I think everybody in the Sept lab knows that the chemical reaction is kind of a transformation of some reactants into products, and usually we represent that. We represent this kind of, as chemists, we represent it by a chemical reaction, which is like examples. Sorry, before we go to that one, examples of chemical reaction is the fermentation of sugar to give you alcohol and carbon dioxide. That's a reaction. Burning of wood or trees, it involves also combustion reaction, and it is a reaction. You're changing wood into both CO2 and water. All of these are examples of chemical reactions. Now, usually we represent a chemical reaction instead of saying, oh, I get those sugar and I put it in fermentation and I get alcohol and that thing. We usually represent it by molecular formulas in there, or the atomic formulas, and we represented those being the reactant, what we started with, and that arrow tells you from where that we're going from A to B plus C. Sometimes you would see something like this later on, and that tells you that the reaction is going both ways, both sides, and you're going to learn about this in Chem 112, about equilibrium, chemical equilibrium, and B and C are the products in there. So this is how we usually represent those. Now, most of the time, or all of the time, we have to represent between two brackets, what is the state of this matter? Is it liquid when you're doing the reaction? Did you start with the reactant in the gas phase, in the liquid phase, or in the solid phase? So if you use L, for example, then I know that A was liquid or is liquid when you started the reaction, or you used it in the liquid. When it was liquid, you didn't, for example, if it is metal, you didn't melt it, or you melted, what exactly you did. So B, also we can either put S, that means it's a solid. If I put G, that's a gas. Those are the notations that we use, and usually whenever we're writing a chemical reaction, at least when we get started with chapter 4, we have to represent those numbers. We have to represent those states as we go in a reaction. Okay? So this is kind of in a written form what I just said. This is the state. The only state that I didn't talk about is aqueous. And when I say aqueous, it means something dissolved in water, that the reaction is going in water. Both the reactants and the products are done in water. We're doing the reaction in water. This is what AQ means. And we're going to talk in chapter 4 all about those reactions which happens in water. Okay? Now, the first law that we need to go further in the chemical reaction is the law stated by Lavoisier, which states that matter can be neither destroyed nor created. That means if I put in a beaker 2 milligrams or 2 moles of magnesium, at the end of the reaction, I'm going to find 2 milligrams or 2 moles of magnesium. It can be in another form. It could be, for example, it went from magnesium to magnesium 2+, or it is now in a compound, magnesium oxide. But at the end of the reaction, I'm going to find the same amount of magnesium. It's not going to disappear. It's not suddenly I'm going to get tin inside or for example, mercury inside the beaker. If I started with magnesium and oxygen, I'm going to end up with magnesium and oxygen of the same amount. And because of this law, we get to the point that we balance equation. We do the balance of a chemical equation, which I think most of you learned in high school, which is if I have something like this, iron plus oxygen, and it gives me iron oxide, then you begin balancing the equation and saying, okay, I have the amount that I have on the left on the product side, I should have exactly the same amount in the reactant sides. And that goes back to that law, the conservation of matter. That matter can neither be destroyed or created. Otherwise, you can't do this balancing. So here I have 2Fe. So I'm going to put 2Fe in here. I'm going to have 3, and there's 3 oxygen, but I have 2 here, so I'm going to put 3 over 2, because 3 over 2 times 2, 3 over 2 times 2, 2 gonna cancel 2, you end up with 3, okay? Now, this, putting the fraction in here is not wrong. It's not wrong to put it 3 over 2, but usually the better way, the recommended way that you kind of write your equation is without the fractions in there. So what I'm gonna do to get rid of this 2, I'm gonna multiply the whole equation by 2, just to get rid of that 2. And it's going to be FeS plus 3O2 gas 2 Fe2O3 salt. So in exams, I would always represent it in the recommended way, this way. So that one is not wrong. It's not like sometimes you will see even in papers published in journals or anywhere out there, or even in your book and our book. In any book out there, you may see fractions, but the recommended way is this one. Now, the numbers that you see in here, like this number, and this number, we call these the stoichiometric coefficient of the reaction, of the chemical reaction. And those are very important, and we're going to see in a minute why they are important, why these numbers, why do we care even to balance an equation, okay? So let's get started with some examples of balancing an equation, just to make sure that everybody gets the idea in case you didn't cover that in high school. What I'm going to do, I'm just going to kind of skip those 2 slides, because we're going to cover it on Monday. I'm going to skip those 2 to do the balancing equation, then we'll get back to those. So the question is, tell me what is the stoichiometric coefficient after you balance the above equation, this equation. And the system is 1, 2, 3, guys, numeric, so you have to refresh your iClicker. So hit the refresh button before you send your answer. And the answer should be 1, 2, 3, not A, B. Okay? I think you're right. And they stop it at 1. You can talk to each other, you can talk to the person behind you, next to you. Okay, I only have 40 responses. Do you need some more time? Okay, so I'm going to stop it at 2 minutes. Okay, so I'm going to stop it and check is the most popular answer. I have 3 to be 60%. Yes, 3 is the right answer. Okay, so let's get started with balancing this equation. And I'm going to insert it here and rewrite it somewhere in here. Okay, so usually when I'm balancing the equation, I wouldn't start with oxygen, especially when it is a combustion reaction. That means when I'm putting something and burning it with oxygen. Because I have oxygen in 2 places. So if I balance one, it's gonna be affected by the number of carbons, and if I balance this or I take the number as granted, or that's the right number of oxygen, it's gonna be affected by the number of hydrogen. So when I do the balance for such kind of equations, I wouldn't do the element that is found in in 2 places or 3 places. I would start with the element or the atom that is found in 1 place only. For example, I would start with carbon. I wouldn't start with oxygen. So I have 2 carbons in there. So I'm going to put 2 here. Then I have 5 plus 1. I have 5 hydrogen here and 1 hydrogen. So I have 6 hydrogen. I have 2 here, so 3 times 2. So that's adding me up with 6 hydrogens, 2 carbon. That sounds good. Now let's see the oxygen. Now I have, after I balance the carbon, I would look to the product side, because now the oxygen in this side is already balanced. The one that is not balanced is those 2 oxygens in here. This one and this in here. Okay? Now I have 2 times 2, I have 4 oxygens, 3. So I have total of 7 oxygens here. So 7 oxygen, I have 1 oxygen here and 2 oxygens there. So if I take into consideration this 1 oxygen, so I end up with 3 oxygens in there. Okay? And those circles, I should do this so that nobody thinks it's a 20 or 10. I apologize for that. So 7, I have 7 minus 1, I ended up with 6. I have 2 oxygens here, so if I put 3 there, it will be 6 oxygen. But I don't stop there. I double check everything in my equation before I go any further or say, oh, this is the balance of the equation. I'll go back and check. I have 2 carbons, 2 carbons. I have 6 hydrogen, 3 times 2, 6 hydrogens, 1 oxygen plus 6. So I have 4 and 3. So yes, now it is balanced. I'm sure that, oh, this is the answer. I'll send that this is my answer. Okay? So this is just a little bit more complicated than what we saw a minute ago, just because we have the hydrogen in 2 places and we have the oxygen in 2 places, in both the reactant side and the product side. Again, if my guess that most of you in high school have practiced a lot about that, about balancing equation. In case you did not, you have to practice on OWL. If you have any questions, just pass by my office hour if you're behind in balancing equation, and I can spend as much time as you want with you, okay? To show you how to balance chemical equations. Okay. Okay, we still have 4 minutes. The following is the reaction of magnesium nitride and sulfuric acid. Determine the amount of H2SO4 consumed and the amount of magnesium sulfide produced when 3.5 mole of magnesium nitride reacts. So how are we going to handle this? So my first step, okay, I'm going to give you 1 minute to reread the question. And think about a strategy. How would you solve such a question? So the first step that should come to your mind, guys, is balancing the equation. Okay? First, balance the equation, then you go any further with that. So let's start with balancing the equation. Plus H2SO4 AQ magnesium plus ammonium 2 sulfur. So I'm going to start with the magnesium. I have 3 magnesium in here, and this is magnesium in there, so I'm going to put 3 magnesium there. Nitrogen, I have 2 nitrogen. There are 2 nitrogens there. Now I'm going to hydrogens. I have 2 hydrogens. To this side, I have 8. So I'm going to multiply this by 4 to balance the number of hydrogens. 4 sulfurs, I have here. Okay, so I have 4 sulfurs in here. I have sulfur in 2 places. I have 1 sulfur in this compound and 3 times S. I have 3 sulfurs there. So the number of sulfurs is balanced. Now oxygen, I have 4 times 4. I have 16 oxygen there. Then I have 3 times 4, 12. Plus 4, I have 16. So now the equation is balanced. I can go further with that. Now the question is, determine the amount of H2SO4 consumed and the amount of magnesium produced. Let's first start with how many H2SO4 consumed and the amount when a 3.5 moles of magnesium nitride reacts. First of all, what does those numbers 1, the stoichiometric coefficient 1 and 4 means in this equation? It means that for each 1 mole of magnesium nitride, I need 4 moles of H2SO4. That means if I have for each 1 mole, I need 4 moles of H2SO4. Now it's asking me if you have 3.5 moles of magnesium nitride reacted, how much H2SO4 reacts? So definitely I have to take the stoichiometric coefficient into consideration. So if I started if 3.5 moles of magnesium nitride reacts, that doesn't equal to the number of moles of H2SO4 reacted. Why? Because this equation is telling me for each 1 mole of magnesium nitride, I need 4 of those. And the way to take that into consideration is by doing that for each 3.5 moles, how much of magnesium 3 nitride for each 1 mole, I'm taking the stoichiometric coefficient for each 1 mole of magnesium 3 nitride N2, I need 4 moles of H2SO4. I'm consuming 4 moles and I'm taking the stoichiometric coefficient there. Now, if you want to think about dimensional analysis, this is going to cancel that, and now you have the number of moles of H2SO4, which is 4 times 3.5 moles equal to 14 moles of H2SO4. So this is how we calculate how much consumed. We have to take into consideration the stoichiometric coefficient. And this is why we care about balancing chemical equation, because we're going to take those stoichiometric coefficients into consideration. Okay? Enjoy your weekend, and I'll see you Monday.